Hey everyone, and welcome back for another deep dive. Today we're going to be tackling unsupervised learning.
Ooh, fun.
Yeah, it's going to be a good one.
I love unsupervised learning.
Yeah, it's really cool stuff. So, for anyone who doesn't know, this unsupervised learning is basically like that branch of machine learning where the
Right.
algorithms are kind of like detectives working a case with
Mhm.
nothing but like a bunch of scattered clues around.
Yeah, you just throw a ton of data at it and hope for the best.
Yeah, exactly. And it's all about uncovering hidden structures
Right.
in data that hasn't been neatly labeled
Oh,
for us.
like nicely packaged up in a bow. No, no, no. This is,
Exactly.
yeah, messy.
And so our mission today is to get you up to speed on three key techniques in this field. K-means clustering,
Okay.
principal component analysis,
Yeah,
and association rule learning.
those are the big ones.
Yeah, so buckle up because these techniques, seriously, they pop up everywhere.
Everywhere.
From how companies target ads to how self-driving cars navigate the world.
Self-driving cars, how do they use it?
So self-driving cars, they use it to process the sensor data. So
Oh,
all that visual data and all the data from like the LiDAR and all that,
okay.
they use it to like cluster different objects together so they can tell like, okay, that's a pedestrian,
Yeah,
that's a car, that's a tree and stuff like that.
that makes sense. Yeah. It's really cool how these algorithms can just figure things out on their own, you
Yeah.
know? Like we're not giving them any labels or instructions. It's just, here's a pile of data. Go find something interesting.
Exactly. Yeah. And that's what's so powerful about it, right? We don't have to pre-program all this knowledge into it. It can kind of figure it out on its own.
Mm-hmm.
Okay, so let's start with k-means clustering.
Right.
What comes to mind for you when you think of k-means? I always picture like a giant bowl of colorful marbles that need to be sorted, but like with no instructions on how to do
I love that image. It's
it.
so true. It's like you just have this big jumbled mess
Mm,
and need to make sense of it. And that's exactly what k-means does. It groups similar things together,
right.
like those marbles.
Mhm.
But instead of color, we're looking at similarities in data points.
Okay.
Think of like how streaming services like Netflix suggest movies based on your viewing history.
Oh, yeah.
They're essentially using a form of k-means to cluster viewers with similar tastes
That's really cool.
and then recommend movies that other people in that cluster enjoyed.
I see.
It's like saying, hey, if you like these movies, you might also like these, because other people who like the same movies as you also like these.
So it's more than just grouping, right? It's like predicting what you might like
Yeah,
based on who you're similar to.
exactly.
That's pretty clever. But how does it actually work? Does the algorithm like just randomly throw data points into groups and like hope for the best?
Not exactly.
Yeah.
It's actually a bit more strategic than that. Think of those marbles again,
Mm-hmm.
but let's say we scatter them on a table,
Okay.
and you want to divide them into, let's say, 5 groups. You'd probably start by like picking 5 different marbles, each one representing the center of a group, right?
Yeah, that makes sense. You'd sort of like build out from those starting points.
Exactly. That's what k-means does. It starts with randomly chosen centroids, which are basically like those initial marbles you picked.
Okay.
Then it assigns each data point to the cluster whose centroid is closest.
So like each data point kind of gets pulled towards its nearest centroid, forming a cluster.
Exactly. And once all the data points are assigned, the algorithm recalculates the position of each centroid based on the average position of all the points in that cluster.
Okay.
It's like finding the center of gravity for each group of marbles. Then you just keep repeating those steps.
Okay.
Points get reassigned, centroids shift, until eventually the clusters stabilize
Yeah.
and the centroids stop moving so much.
So it's like a dance almost, with
And
the data points and centroids kind of constantly adjusting until they find a harmonious balance.
yeah, I like that. It's a dance of data.
It's amazing how such a seemingly simple concept can be so effective at like uncovering hidden structures in data.
I know, right?
But there's got to be some challenges, right? Like not all data is as neatly grouped as a bowl of marbles.
No, definitely.
Good.
There are some limitations.
Yeah.
One of the biggest is that you need to tell the algorithm how many clusters you're looking for beforehand. That k value in k-means.
Oh, right, right.
And if you pick the wrong number, you might force the data into clusters that don't actually make sense or miss some subtle groupings that are actually there.
So it's not a set it and forget it kind of algorithm. You need to have some understanding of the data and what you're looking for to use it effectively.
Absolutely. And another challenge is that it can be sensitive to where those initial centroids are placed. If they start in a bad spot, the algorithm might get stuck in a not-so-great solution.
It's like starting a puzzle with the wrong pieces in the wrong place. It can
Oh,
throw everything off.
exactly.
So K-means it's a great tool, but like any tool, it's best used with a skilled hand.
Well said. And sometimes we need to go beyond just grouping things. We need to simplify the data itself before we even start clustering. And that's where principal component analysis, or PCA, comes in.
Ooh, PCA. Now that's one of those techniques that can sound really intimidating at first. What's your go-to way to explain it without getting too lost in like all the math?
Okay, so imagine you're trying to analyze customer data,
Yeah.
right? And you've got like hundreds of variables: age, income, purchase history, browsing habits. The list goes on forever.
Right.
Trying to visualize all of that at once would be impossible, wouldn't it? It'd be like trying to make sense of a 100-dimensional object.
Yeah, my brain is already hurting just thinking about it.
Right. So PCA helps us shrink that dimensionality down to something more manageable.
Okay, so PCA helps us shrink that dimensionality down to something manageable.
Exactly. And the key here is that it does this without losing the most important information.
Okay.
PCA finds the directions of greatest variance in the data. You can think of these as the main axes along which the data is spread out.
Okay.
Like if you had a cloud of data points, it's finding the backbone of that cloud and then projecting everything onto that backbone.
Okay, so instead of looking at hundreds of individual variables, we're creating like a smaller set of super variables
No.
that capture the most important trends in the data.
Exactly. Those are called principal components, and they're basically linear combinations of the original variables. And what's really cool is that they're ordered by how much variation they explain.
I see.
The first principal component captures the most variation, the second captures the next most, and so on.
So it's like ranking the variables by their influence on the overall data set.
Yeah,
And by focusing on just the top few principal components, we can simplify the data without losing too much detail. It's almost like compressing a file, but without sacrificing the essential information.
that's a great way to think about it.
But how does this finding the backbone thing actually work? Are there like tiny little algorithms crawling through the data looking for the most stretched out parts?
Uh-huh. I love that image. But the actual process is more mathematical. It involves calculating something called the covariance matrix, which measures how much each pair of variables changes together. And then we use a technique called eigendecomposition to find what are called the eigenvectors and eigenvalues of this matrix.
Eigenvectors, eigenvalues. Those sound like something straight out of Star Trek.
They do sound kind of sci-fi, right? But they're just mathematical concepts that help us find those principal components. Think of eigenvectors as the directions of those backbone axes and eigenvalues as a measure of how much variation is captured along each axis.
Okay, so the eigenvectors point us in the right direction, and the eigenvalues tell us how important those directions are.
Exactly.
It's starting to make more sense. So we've shrunk our data down to a manageable size. What do we do with it now?
Well, that's where the real fun begins. PCA has so many applications. One of the most common is data visualization. By reducing the data down to 2 or 3 dimensions, we can actually plot it on a graph and see patterns that were hidden before.
Oh, wow. So it's like giving our brains a break by turning this complex problem into something we can actually visualize.
Exactly. But PCA's usefulness goes way beyond just pretty pictures. It's also a powerful tool for noise reduction. By focusing on the principal components, we can filter out irrelevant information, which can actually improve the performance of machine learning models.
It's like clearing away the clutter to get a clearer view of what's important.
Exactly.
Are there any downsides to this data simplification process, though? Do we lose anything important by focusing only on those principal components?
That's a great question, and it is something to be mindful of. PCA works best when the relationships between variables are linear. If the data has more complex, nonlinear relationships, PCA might not capture all the nuances.
Okay, so it's not a one-size-fits-all solution. You need to understand the nature of your data before applying PCA. It's like choosing the right tool for the job.
Absolutely.
But overall, it sounds like an incredibly powerful way to untangle complex data sets and unlock hidden insights.
It really is. And speaking of unlocking insights, our next technique takes a different approach. It's called association rule learning, and it's all about finding those if this then that relationships in data.
Ah, yes. Association rule learning. The technique that makes online shopping so eerily personalized. It's like those algorithms are playing matchmaker with products,
I like that.
figuring out which ones have like a secret crush on each other.
It's true. The goal is to find rules that describe how often items or events occur together.
Okay.
Like think of those customers also bought recommendations you see on e-commerce sites.
Oh, yeah.
They're using association rule learning to suggest products based on what other people who bought similar items also purchased.
Right, like that classic example of beer and diapers being bought together.
Exactly. While the truth behind that specific example is debatable, it really illustrates the point. By analyzing large data sets of transactions, we can uncover hidden patterns that might not be obvious at first glance.
So it's more than just making shopping recommendations. It's about understanding customer behavior and finding those unexpected connections that can inform business decisions.
Absolutely.
Pretty clever.
And the applications go way beyond retail. Think about healthcare, for instance. Association rules could be used to identify potential risk factors for certain diseases.
Oh, wow.
Or in finance, they could help detect fraudulent transactions. The possibilities are endless.
The possibilities are endless. That's amazing. But before we get too carried away, let's break down how these association rules are actually discovered, because I'm picturing like this giant web of connections between data points, and it's making my head spin.
Yeah, it can get pretty complex. There are a few key metrics involved that help us make sense of it all. One is called support, which measures how frequently a particular item set like beer and diapers appears in the data set.
Okay.
The higher the support, the more common the association.
So if we see bread and butter appearing together in a lot of shopping carts, that would have high support.
Exactly. Then we have confidence, which tells us how likely it is to find item B, given that we already know item A is present.
So if someone buys bread, how confident are we that they'll also buy butter?
Precisely. And then there's lift, which tells us how much more likely we are to find items A and B together than we would expect if they were completely independent.
Ah, so lift helps us separate genuine connections from just mere coincidences.
Yeah.
We're not just looking for things that happen to appear together sometimes, but those with a real underlying link.
Exactly. And this is crucial because we don't want to base decisions on spurious associations.
Yeah.
It's like the difference between correlation and causation. Just because two things happen together doesn't mean one causes the other.
Right, like ice cream and sunburn. They often occur together, but one doesn't cause the other. It's the hot weather that drives both.
Exactly. So in association, rule learning lift helps us avoid those misleading correlations.
I see. That makes a lot of sense. This is fascinating stuff. But before we get too lost in the world of association rules, let's take a step back and consider the big picture. We've explored these three really powerful techniques for uncovering hidden patterns in data, each with its strengths and limitations, but all incredibly useful for making sense of like this increasingly data-driven world we live in.
You said it. I think it's amazing how much we can learn from data when we let the algorithms do the heavy lifting.
It really is. And as we move into the next part of our deep dive, we'll explore how these techniques are being used in the real world.
Oh yes, the applications are just incredible.
I can't wait to hear about it. So everyone grab your data mining helmets and we'll see you in part 2.
See you there.
Welcome back, everyone. In the last part, we dug into 3 key techniques in unsupervised learning: K-means, clustering, PCA, and association rule learning. Now I'm itching to hear about how these techniques are actually used to solve real-world problems. What are some of the most exciting applications you've come across?
Oh, where do I even begin? The applications are so diverse. One area that I always find fascinating is how unsupervised learning is being used in healthcare.
Ooh, healthcare.
Yeah. For instance, researchers are using K-means clustering to identify subtypes of diseases
Okay.
that might not be apparent just from looking at symptoms.
So instead of treating everyone with the same diagnosis, the same way they can tailor treatments based on these like more subtle groupings.
Exactly. It's all about moving towards more personalized medicine.
That's amazing.
And PCA is playing a huge role in medical imaging. By reducing the dimensionality of complex scans like MRIs,
Okay.
PCA can help doctors identify subtle abnormalities that they might otherwise miss.
That's incredible. It's like giving doctors a magnifying glass to see those hidden details.
Right.
It sounds like unsupervised learning is revolutionizing how we diagnose and treat diseases.
Yeah.
What about other fields, though? Where else are these techniques making a big impact?
Well, finance is another hotbed of activity.
And-
Banks and financial institutions are using association rule learning to detect fraudulent transactions.
Oh, yeah.
By analyzing patterns in spending behavior, they can identify anomalies that might signal fraud. It's like having a virtual detective constantly monitoring your account.
That gives me a sense of security just thinking about it. I know online retailers use similar techniques to detect fraudulent purchases. It's amazing how these algorithms can sift through mountains of data to find those needles in the haystack.
Absolutely. And it's not just about identifying bad actors.
Yeah.
Unsupervised learning is also helping businesses understand their customers better.
Okay.
Marketers are using clustering techniques to segment customers into different groups based on their purchasing habits, demographics, even social media activity.
Oh, wow.
This allows them to tailor their marketing campaigns and product offerings more effectively.
So instead of blasting everyone with the same generic ads, they can target specific groups with messages that are more likely to resonate.
Exactly. It's about making marketing more relevant and less intrusive. And this same idea applies to recommender systems, streaming services, e-commerce sites, even news apps. They all use unsupervised learning to personalize recommendations and create those just-for-you experiences.
It's like having a personal shopper or curator who knows your tastes better than you do. But it's not just about improving business or making our lives more convenient. Are there applications of unsupervised learning that are tackling bigger challenges?
Absolutely. One area where unsupervised learning is showing immense promise is in environmental science.
Oh, wow.
For instance, researchers are using clustering algorithms to analyze climate data, helping us understand patterns in weather events and make more accurate predictions about climate change.
Wow, that's incredibly important work. So unsupervised learning is helping us understand the complex systems that govern our planet.
Exactly. It's also being used to monitor deforestation, track the movement of endangered species, and even optimize the placement of renewable energy sources.
It's inspiring to see how these techniques are being applied to address some of the most pressing challenges facing our world. But I imagine there are also challenges in using unsupervised learning, especially when dealing with complex real-world problems.
You're right, there are always challenges. One of the biggest is dealing with noisy data. In a perfect world, our data would be clean and well-structured.
Mm,
But in reality, data is often messy, incomplete, or even inaccurate.
right.
And this can really throw off unsupervised learning algorithms, leading to inaccurate or misleading results.
So it's like trying to solve a puzzle where some of the pieces are missing or don't quite fit together.
Exactly. That's why data preprocessing is such a crucial step in any unsupervised learning workflow. We need to clean the data, handle missing values, and format it in a way that the algorithms can understand.
It's like preparing the ingredients before you start cooking. If your ingredients are bad, your dish won't turn out well, no matter how good a chef you are.
That's a great analogy. And then there's the challenge of interpreting the results.
Yeah.
Unsupervised learning algorithms can churn through data and spit out clusters, principal components, or association rules.
Ugh.
But what do they actually mean?
Yeah.
How do we translate these findings into actionable insights?
Right, because a bunch of numbers and labels don't mean much if we don't understand what they're telling us about the underlying phenomenon.
Exactly. That's where domain expertise comes in. We need people who understand the data, the context, and the problem we're trying to solve to make sense of the output of these algorithms.
It's like having a translator who can bridge the gap between the language of data and the language of human understanding.
Perfectly put. It's this collaboration between data scientists, domain experts, and decision makers that unlocks the true potential of unsupervised learning.
It sounds like a powerful team. But even with a great team, there's always the risk of misinterpreting the results or drawing faulty conclusions, right?
Absolutely. It's crucial to remember that unsupervised learning is a tool, and like any tool, it can be misused.
Yeah.
One of the most common pitfalls is overfitting the data. This happens when the algorithm learns the training data so well that it doesn't generalize well to new, unseen data.
It's like memorizing the answers to a test instead of understanding the concepts. You might ace that specific test, but struggle with anything new.
Exactly. To avoid overfitting, we need to use techniques like cross-validation, where we train the algorithm on a subset of the data and then test it on a separate unseen subset.
Oh, right.
This helps us ensure that the model is generalizable and not just memorizing the quirks of the training data.
So it's like giving the algorithm a practice test before the real exam to make sure it's actually learning and not just cheating.
That's a great way to put it. But even if we avoid overfitting, there's still the challenge of interpreting the results in a way that aligns with our goals and values, right? Unsupervised learning algorithms don't have any inherent understanding of ethics or fairness. They simply find patterns in the data, regardless of whether those patterns are beneficial or harmful.
Right.
It's up to us, the humans using these tools, to ensure that the insights we glean are used responsibly and don't perpetuate biases or lead to unintended consequences.
That's such an important point. It's like having this powerful engine. It can propel us forward, but if we don't steer it carefully, it can also lead us astray.
Well said. It's this awareness of the potential pitfalls combined with a commitment to responsible use that will allow us to truly harness the power of unsupervised learning for the benefit of society.
That's a perfect segue into the next part of our deep dive. We've explored the how and the why, but now I'm curious about the what's next. Where is unsupervised learning headed? What exciting developments are on the horizon?
Oh, there's so much to be excited about. One area that's really heating up is the intersection of unsupervised learning and deep learning.
Deep learning.
Yeah, deep learning, with its ability to learn complex patterns from massive data sets, is opening up all sorts of new possibilities for unsupervised learning.
Deep learning, I know it's been making waves in other areas of AI, like image recognition and natural language processing. How does it fit into the world of unsupervised learning?
It's like giving unsupervised learning a turbo boost. Deep learning models, with their multiple layers of interconnected nodes, can capture nonlinear relationships in data that traditional unsupervised learning methods might miss.
So it's like upgrading from a magnifying glass to a high-powered microscope, allowing us to see even finer details and make more nuanced distinctions in the data.
That's a fantastic analogy. This combination of deep learning and unsupervised learning is leading to breakthroughs in areas like anomaly detection. For instance, in cybersecurity, these hybrid algorithms can be used to identify subtle patterns in network traffic that might signal a cyber attack.
It's like having a virtual bloodhound sniffing out those faintest traces of malicious activity. I can see how that would be incredibly valuable in protecting our digital infrastructure. What other applications are emerging from this deep learning, unsupervised learning fusion?
One that I'm particularly excited about is generative modeling.
It's generative modeling.
Yeah, generative models are deep learning algorithms that are trained to generate new data that resembles the training data.
So it's like teaching a computer to be an artist. It learns from existing paintings and then creates new ones based on its understanding of style and composition.
Exactly. This has incredible potential in creative fields like music, art, and even writing. Imagine algorithms that can compose new symphonies or write screenplays, but the applications go far beyond the arts.
Oh, wow, that's mind-blowing. Where else are generative models making a splash?
One promising area is drug discovery. Researchers are using generative models to design new molecules with specific properties, potentially accelerating the development of new drugs and therapies.
It's like having a virtual chemist exploring a vast chemical space to find those elusive molecules that could revolutionize medicine.
Exactly. And in manufacturing, generative models are being used to optimize designs, leading to lighter, stronger, and more efficient products.
It's like having a virtual engineer constantly iterating and improving upon designs, pushing the boundaries of what's possible. These applications are truly remarkable.
They are. And as these technologies continue to evolve, we can expect even more groundbreaking applications to emerge. It's an incredibly exciting time to be working in this field.
I can only imagine. It feels like we're just scratching the surface of what unsupervised learning can achieve. But before we get too swept up in the future, let's take a moment to recap what we've learned so far.
Okay, sounds good.
We've covered a lot of ground. We started by diving into three key techniques in unsupervised learning: K-means, clustering, PCA, and association rule learning. Then we explored how these techniques are being applied to solve real-world problems in fields like healthcare finance marketing and environmental science. We also talked about the importance of data pre-processing, careful interpretation of results, and the need for collaboration between data scientists and domain experts to unlock the true potential of these techniques.
Right, all essential stuff.
And we touched on some of the challenges in using unsupervised learning, such as dealing with noisy data, avoiding overfitting, and ensuring that the insights we gain are used ethically and responsibly.
Important considerations for sure.
It's been an incredible journey so far, but there's one more leg of our deep dive to explore. We've talked about the how, the why, and the what's next, but now I'm curious about something a bit more philosophical. What does it mean for a machine to learn without explicit instructions? Can these algorithms truly understand the data they're analyzing, or are they simply sophisticated pattern matchers?
Ooh, those are great questions. And that's exactly what we'll be delving into in the final part of our deep dive. We'll explore the limits of machine learning, the nature of intelligence, and the potential for true artificial understanding.
Sounds like we're about to get philosophical. I can't wait. Everyone join us for the grand finale of our unsupervised learning adventure. Welcome back, fellow data explorers. We've journeyed through like the technical landscape of unsupervised learning.
This has been quite a journey.
It really has. We've explored its real-world applications, and now, as promised, we're taking that philosophical turn.
All right, let's get philosophical.
You know, it's fascinating to me to think about these algorithms crunching all this data, finding patterns, even like generating new data, all without any explicit instructions.
Right.
It makes me wonder, like, what does it truly mean for a machine to learn without a teacher? Is it just sophisticated mimicry, or is there like a deeper level of understanding going on?
That is the million-dollar question, isn't it?
Yeah.
And it's one that has philosophers and computer scientists kind of scratching their heads.
Yeah.
On the one hand, these algorithms, they can do some pretty remarkable things.
Right.
They can sift through these massive data sets, identify subtle correlations, and even create outputs that look a lot like human creativity.
Yeah.
But on the other hand, their learning is fundamentally different from how we as humans learn.
It's like they're playing a different game altogether, right?
Yeah.
They might be masters at finding statistical relationships, but do they actually grasp the meaning behind those relationships? Like, do they understand the why behind the what?
That's the heart of the debate right there.
Yeah.
Take, for example, an algorithm that's been trained to predict traffic patterns based on historical data.
Okay.
It might be incredibly accurate in its predictions,
Yeah.
but it doesn't actually understand the reasons for those patterns.
Yeah.
It doesn't know about things like rush hour or school holidays or special events that might influence traffic flow.
Right.
It's simply learned to associate certain time periods and weather conditions with higher or lower traffic volumes.
So it's like they're missing that layer of context, like that common sense understanding of the world that we humans just take for granted.
Exactly. They might be able to predict what will happen, but they don't truly comprehend why it's happening.
Right.
They lack that ability to reason abstractly, to connect the dots in a way that makes sense beyond the data itself.
Yeah.
They're operating within a closed system defined by the data they've been trained on, whereas human understanding is so much more open-ended, adaptable, and informed by a lifetime of experiences and interactions with the world.
It's like the difference between memorizing a recipe and truly understanding the culinary principles behind it.
Oh, I like that.
You might be able to follow the instructions and bake a decent cake,
Yeah.
but you wouldn't be able to improvise or adapt or create something truly novel without that deeper understanding.
That's a great analogy, and it really highlights a key limitation of current artificial intelligence.
Okay.
It excels at tasks that can be clearly defined and broken down into a series of steps,
Right.
but it struggles with tasks that require things like intuition, creativity, or an understanding of complex social dynamics.
So while these algorithms can be incredibly powerful tools, we need to be mindful of their limitations. It's not about seeing AI as like a threat or a replacement for human intelligence.
Right.
It's about recognizing its strengths and weaknesses and finding ways to leverage it effectively while still valuing those uniquely human qualities that make us who we are.
I could agree more. It's about embracing this collaboration between humans and machines.
Yeah.
Each brings its own unique strengths to the table.
Mm.
Algorithms can process vast amounts of data, identify patterns, and automate tasks with incredible speed and accuracy.
Right.
Humans, we bring creativity, critical thinking, emotional intelligence, and that ability to connect the dots in a way that machines just can't.
It's like a partnership where each side complements the other.
Exactly.
We can leverage the power of algorithms to enhance our own abilities, and in turn, we can guide the development and deployment of these technologies in a way that aligns with our values and our goals.
Absolutely. It's about
True.
creating a future where humans and machines work together, not against each other, to solve complex problems, create new possibilities, and build a better world. And that, I think, is a pretty inspiring note to conclude our deep dive.
I couldn't agree more. We've journeyed from like the technical details of algorithms to the philosophical implications of AI, and it's been an incredible exploration.
It has.
I hope you, our listeners, are walking away with a newfound appreciation for the power, the potential, and the responsibility that comes with unsupervised learning.
I hear so too.
Until next time, keep those data neurons firing, and remember, the quest for knowledge is a journey best shared.